How does a single operator in a control room monitor and control hundreds of sensors, pumps, and valves spread across an oil pipeline that is 1,000 kilometers long? The answer is SCADA. By the end of this video, you will understand what SCADA is, how it collects data from remote field sites, and why it is the backbone of critical infrastructure around the world. SCADA stands for Supervisory Control and Data Acquisition, a system that gathers real-time data from geographically dispersed equipment and presents it to operators so they can supervise and control industrial processes from a central location. SCADA systems are the nervous system of modern infrastructure. In the oil and gas industry, they monitor pipeline pressures, pump station flows, and compressor speeds across thousands of kilometers. In power utilities, they balance load between substations and control circuit breakers in real time. Water treatment plants use SCADA to manage intake pumps, chemical dosing, and reservoir levels. Manufacturing facilities use it to supervise production lines. If a critical process spans multiple geographic locations and needs centralized visibility, SCADA is the technology that makes it possible. Every SCADA system has 4 essential components. First, field instrumentation, sensors, transmitters, analyzers, and actuators installed at the physical process. These are the eyes and hands of the system. Second, remote terminal units, or RTUs, and programmable logic controllers, or PLCs. These are the local intelligence at each remote site. They read sensors, execute control logic, and communicate upward. Third, the communication network, radio, satellite, cellular, fiber optic, or leased line, which carries data between the field and the control center. Fourth, the SCADA master station, the HMI servers, historian, alarm system, and operator consoles where everything is displayed and controlled. The remote terminal unit is the field brain of a SCADA system. At a remote pump station, the RTU connects to pressure transmitters, flow meters, motor current sensors, and valve position feedback. It scans these inputs continuously, converts the analog signals to digital values, stores them locally, and transmits them to the SCADA master on a schedule or on exception, meaning it reports immediately when a value changes beyond a threshold. The RTU also receives commands from the master: open valve, start pump, change set point. In many modern installations, an intelligent electronic device, or IED, or a PLC with SCADA connectivity performs the same role as a traditional RTU. SCADA systems were historically built on proprietary protocols, but 2 dominate modern installations. Modbus, developed in 1979, is still widely used for serial communication between RTUs and the SCADA master. DMP3, the Distributed Network Protocol, was designed specifically for utilities and adds reliable delivery, timestamping, and event reporting to Modbus-style communication. For modern IP-based SCADA networks, OPCDA and OPCUA provide standardized data exchange between SCADA servers, historian databases, and business systems. The communication protocol defines how data is packaged, addressed, and error-checked. Getting it wrong means lost data or incorrect values at the control room. The SCADA master station is the control room brain. It polls all RTUs on a regular cycle, collecting current values of every tag in the system: pressures, flows, temperatures, valve positions, alarm states. The HMI software displays this as mimics, graphical representations of the process that update in real time. When a value exceeds a limit, the alarm system alerts the operator. The historian server records every tag value with a timestamp, creating an archive that engineers use to analyze performance and diagnose faults. Some SCADA systems include advanced control functions like set point optimization or automatic load balancing, but the primary role of the master is supervisory, presenting information and accepting operator commands. Quick check before we continue. If the SCADA master loses communication with a remote RTU, what should the operator do first? Think about it. The answer: Check the communication path, radio, cellular modem, or fiber, before assuming a field failure. Lost communications means the HMI freezes at last known values. The process itself may still be running normally under local RTU control. SCADA and DCS are often confused, but they solve different problems. A DCS, or distributed control system, is designed for continuous process control in a single facility, a refinery, a chemical plant. It has tight, deterministic control loops running in milliseconds and high-bandwidth communication between controllers and I/O modules in the same cabinet room. SCADA is designed for wide-area supervisory monitoring where the distances are too great for direct wiring and the communication bandwidth is limited. A SCADA scan cycle might be 1 second to several minutes, while a DCS loop executes in 100 to 500 milliseconds. Both can coexist in the same facility. A refinery might have a DCS for process control and a SCADA system to monitor a remote off-site storage terminal. Here is what most SCADA diagrams do not show. The polling architecture determines what you see and how fast you see it. A SCADA master typically polls each RTU sequentially in a round-robin cycle. If you have 50 RTUs and each takes 200 milliseconds to respond, your full system update cycle takes 10 seconds minimum. Exception reporting changes this. The RTU only transmits when a value changes beyond a deadband, reducing communication load, but introducing the risk that slow changes are missed. Timestamping at the RTU solves the time skew problem. Even if data arrives late at the master, the historian records the event at the time it actually occurred at the field device. This distinction between polling time, event time, and display time is critical for alarm analysis and incident investigation. SCADA systems were designed for reliability and remote visibility, not cybersecurity. Early systems ran on isolated radio networks where physical access was the only real threat. Today, SCADA systems are increasingly connected to corporate networks and the internet, creating attack surfaces that did not exist before. The 2021 Aldsmar water treatment plant attack is a stark example. An attacker gained remote access to the SCADA HMI and attempted to increase sodium hydroxide concentration to a dangerous level. An operator noticed the cursor moving and intervened manually. SCADA security now requires network segmentation, multi-factor authentication, encrypted communications, and continuous monitoring, the same defensive architecture used in IT, adapted for operational technology. Here is what you now know about SCADA. SCADA stands for Supervisory Control and Data Acquisition. It provides real-time monitoring and control of geographically dispersed industrial processes. The 4 components are field instruments, RTUs or PLCs, a communication network, and the SCADA master station. Common protocols are Modbus, DMP3, and OPC-UA. SCADA differs from DCS in geographic scale, communication bandwidth, and scan cycle speed. The invisible polling architecture determines data freshness and event timing. And SCADA security is now a critical concern as these systems connect to corporate networks and face sophisticated cyber threats. Thanks for watching. If this video helped you understand SCADA, please subscribe for more videos on industrial automation, instrumentation, and OT cybersecurity. Every week, we cover topics that matter to control engineers, instrument technicians, and OT security professionals working in real industrial plants.